Okay, so I'm Richard Milner. I'm a research scientist in business change and innovation at Ordnance Survey. I've worked at Ordnance Survey for about 5 years and have done a range of things, starting out in photogrammetry. And just to give a brief background about myself, I've got a BSc in Geography from University of Liverpool and an MSc from Cranfield University in Geographic Information Management. As well as working on Ordnance Survey, I've also worked for utilities companies and within the forestry sector. And today I'm going to speak to you about point cloud, the future of mapping. I'll go over the next about 20 minutes, I'll go over what we do within my team of business change and innovation, some of the things we're currently doing, not just point clouds, but some of the other things. Then I'll give an overview of what point clouds are for those of you who don't know, because we've got a wide range of people listening today. We'll look at the different ways to collect them, so the different types of systems that you can use. And we'll also look at some of the applications from it. And as Sam mentioned, if people ask questions throughout, I'll do my best to answer some at the end. And if we haven't got time to finish them all, we'll try and feedback and give you more answers in the future. So as I say, I work in business change and innovation, which is a department within Ordnance Survey looking at new technology and seeing if things are market ready. We look at ways to improve efficiency in our way we collect data, investigate new sensors, platforms and processes, and also look at new capacities, the new types of things we could capture. We do a wide range of things within this department, looking at data capture, data integration, image processing, classification, change detection, machine learning, and crowdsourcing. And I'm going to give you a brief overview of before we start talking about point clouds, of the three that are on screen. So, classification. So classification is a way of getting a computer to automatically identify features within an image, so someone doesn't have to always manually go through and find new features. What's up on screen at the moment is a traditional mapping agency type workflow that's been worked for many years. So you have a plane, you capture some imagery, from that you process it to create height products and ortho-rectified imagery type thing, and then this would often be passed over to a photogrammetrist or someone to work with monoplotting to capture vector data from. But the third process we can try and improve by having some automatic processes to improve the speed at which we capture things. So within Ordnance Survey we use eCognition software from Trimble to use object-based image classification. So our input data, as you can see on screen there, is imagery in both ortho-rectified imagery and near-infrared, both from our ultracam camera that flies in our plane, as well as elevation models that are derived, so a DSM and a normalized DSM. So they're surface models, one with the ground and one without the ground. And we're also looking at slope and vector information. Within eCognition, we create a rule set that is completely transferable across the entire country, so it works in both rural and urban urban areas, and it doesn't need any training data. So we've got one rule set, we put our input data, and we're able to produce a classification as shown on the left-hand side, where we've got pink blobs which are showing where buildings are, green is vegetation of different heights, and we've got some ground from that. We use to work out what classifications are, we use colour, height, shape, texture, and quite interestingly, context. So, for example, if I was looking for a building, looking at the colour, it's likely to be red or grey or brown, for example, but not likely to be green. Its height is going to be greater than a metre, but less than 100 metres. Shape, often rectangular, and, for example, with context, it would usually be bigger than the surrounding features and not, for example, within a body of water. So using this process, we found that the targets we're looking for of overall accuracy rate of around 88.5%, but that does vary greatly with the different classes. So this is a good way to automatically collect data. We're then able to take that data out of image classification, which can identify some new products, but use it within our existing topographic data set. So we take the image classification and compare it to our OS master map, which is our topographic data, and see what has changed in a semi-autonomous way. So as you can see with the image in the center there, there's some brightly colored shapes, and they're suggesting things that are changed. So rather than a lot of classification processes that take an image or raster and compare it to a previous one, that would highlight all changes, where by comparing against our topographic data set, we're only finding things that are of interest to us. So we put this through the same rule set and recognition, produce these results, and then these are passed to someone in data capture who will manually verify whether something is true or not. And if it's true, it obviously needs to be updated in MasterMap. So here's an example of two things that have been identified. The red circle is an extension to a building, and the yellow circle showing a new path. These are both correct changes and would be updated, but in this process we have a lot of false positives. A false positive is something that is identified that may not actually be correct. So for example, if there's a temporary building built, we wouldn't want to capture that in our topographic data set, so we would assume that to not be correct. In these false positives, we have a lot of them. For example, we have all the ones we classify in rural areas, 35 to 45% are correct. And we would be able to reduce that to a lower number, but in doing that we may miss some of the accurate classification. So we keep a lot of the false positives in, but are still able to get accuracies of the similar accuracies to a manual sweep, and it does improve efficiency of around 20% in time for capturing the same data. In addition to looking at change detection, we also do things such as machine learning. So here's one of the projects we worked on, which was identifying shapes of roofs of buildings. So they're seeing whether a roof is gabled or flat or a complex shape. For this, we took our DSM, so our elevation model, and cut out the buildings using the footprints. So there's 3 examples of buildings here with different shaped roofs. First of all, we wanted to see if there was any sense in this data, so we did a k-means clustering on it, which sorts all the individual buildings into groups to see whether there is a specific signature that suggests that a building is a certain shape. We found that this was useful and we could do something. So the next step was to train a classifier and then classify. So we have this very bright box here, and this is showing hundreds of roof shapes. This is just a small section because we put in thousands of them. A small section of these were classified manually and were provided as a training data set, which was then put into a neural network, which is a complex way of machine learning what features are. From here you can see on the right it was able to group similar roof shapes into similar features. So we're able to use machine learning to identify roof shapes. Now we're looking into much deeper networks to do more complex things, looking at our extensive image and vector archive to see what we could extract in future to help the way we capture data. So on to point clouds. What are they? This is a question that gets asked a lot. Well, simply, they're unconnected points representing 3-dimensional environments, so just a group of points in 3D space. Historically, these were typically captured from LiDAR, which is when a plane flies over an area, a beam of laser shot down, and the points are returned and collected as points from the ground. These are usually stored in LAS format, but there is a huge number of formats also out there, and they can be just from a small few points for small objects to billions of points that cover vast areas. They contain information not only on position, but can have intensity, classification, and color. And as I mentioned a moment ago, these were typically from LiDAR, but with new sensor development, these are not just from planes or LiDAR. These can now be taken from other sensors. So I'm going to show you through some of the other ways you can capture them. Terrestrial laser scanner. So here we have on the right a picture of a Trimble SX10, which is a laser scanner that can have a camera attached to it. And on the left is an example of the data it captures. So these are static scanners. They sit on a tripod, so they don't move, and the head spins around and collects laser points, which can be combined with the imagery to make a colorized point cloud. I'm going to give you an example now. If I switch over to Chrome browser, here we have the example I was just showing you a picture of an area of Manchester, which is a city in the UK. This I'm going to show you a few examples in this viewer, and this is built on Poetry, and it's a way of streaming data over the internet. So it's a slightly lower resolution than the full scan, and I've added some shaders to bring out some of the detail in some of the details in the scan. But as you can see, I can quite clearly identify buildings, road markings, lampposts, features on the ground. These type of scans can take anywhere from a couple of minutes up to 10, 20 minutes to do, and here's an example of 2 scans being carried out in one place. As it's a busy environment, when the lasers hit things, moving objects such as people and vehicles, these can leave noise in the point cloud that does need to be cleaned out. But even with the noise in, you can still get a good idea of an environment, and these are really high resolution and can be used for a wide range of activities. I continue from static scanners. We've also got a lot of things that are more mobile. So one of the benefits of being mobile is you can capture data more quickly, so you can cover larger areas. But some of these scanners can also be used internally, so that's inside buildings. And obviously you haven't got GPS inside or GNSS because the satellites won't reach through roofs. So most of these systems that you can see on screen use SLAM, which is simultaneous localization and mapping, which is a way of a laser sends out some points, and then you move forward, and as it sends out more points, it looks back and joins the two together, so it makes a continuous trajectory. So it works out where you are in position. So the Zebra Evo on the left is a handheld scanner that uses this SLAM algorithm, and it collects data that you're seeing on screen currently. This is just XYZ data, so just position. There isn't any color or intensity in it, but it's a really fast, lightweight, easy to use system. And if you're looking for specifically geometry, this is a good type of thing to use. And I'll show you some more data in a moment of capturing the building, the Ordnance Survey's head office building that we captured. There's also other systems like the Pegasus backpack at the top on the right there, which is a combined camera, laser and GPS system. So it captures imagery, point clouds, and it can be used with GPS or without GPS. It can transition between inside and outside really well, and it can create colorized point clouds. Similarly, the TIMS-CART, or Trimble's Indoor Mobile Mapping System at the bottom there, captures imagery and laser points, and it also has measurement units in the wheel, so it can accurately work out how far it's traveled to improve its positioning internally. I'm going to show you an example of the CART system as well in a moment. So the first scan I was referring to, the ZEB scan, this interesting shaped building is our head office inside, but seen from the outside. So if I go inside, you can see there's been millions of points captured. So this is into our atrium of our building where we have our restaurant, and you can see some of the balconies going around. And we can just move through the walls and see lots of different areas of the building. This entire building, which is 3 floors, was captured in about 40 minutes. So it gives you an idea of how quickly you can capture huge amounts of data. And as you can see, it all tied together really well. So it's a good way of finding position of things in the building. The TIMS-CART we also brought into the building and scanned it. Obviously this had wheels, and it's quite a sizable system, so it can't be taken upstairs. It could go up in lifts, for example. But what you'll see, the additional benefits from this system is the fact that you're getting a much more detailed scan. You're also getting intensity. And there is also a camera that works with it. When we test it, the camera wasn't tied up with the scanner, so we couldn't create a colorized point cloud from this, but in future this would be a thing that this system would offer, and the Pegasus backpack would also can also carry out this. So from here you can see that, like the static scanner, you can get a huge amount of information. You can capture this really quickly, and it is a great quality way of capturing data on the move. So if you wanted to see, sorry, it may have been a slight delay in the appearance of the inside of the building there, but now you should be able to see inside the building. This is you can see small things such as chairs and people, and down to millimeters of accuracy, and you're able to pick up details that you would otherwise not be able to use. As well as the internal scanners, there are mobile mapping systems. So mobile mapping systems are similar laser, camera, GPS and IMU type systems that can sit on top of cars, boats, and to prove their versatility, I've got an image of the Pegasus Stream, which is on top of ground penetrating radar. So on the right there, we've got a mobile mapping system that's capturing data above ground and a terrestrial system that is capturing data below ground all at once. And these collect along road corridors, so you can drive through a city at around 15 miles an hour, capturing vast quantities of data that really bring this data to life. I'll attempt to show some of Pegasus 2 data now. So this is the mobile mapping system of we've captured of an area of Bournemouth. This is just a small scan, but as you can imagine, you can capture a lot of data quite quickly. That's covering just a mile or so of information, but here you can clearly see that there's details under trees that you can identify. You can identify lampposts, buildings. Once again, it's a bit slow in responding, so in a moment you'll hopefully catch up and be able to see some of the views from the ground. But in essence, this opens up whole new doors of options by being able to capture large areas which could be used to manually capture data or automatically extract things from. Doesn't seem that we'll be able to show fully the details of this scan, but at a later date we can send out some images of the point clouds so people can get a better idea of the type of system.
As mentioned at the beginning, we have recorded this webinar, so if you are unable to see the changes we're doing, it will go through on the recorded version for you to relook at.
Thank you, Sam. I'll go back to PowerPoint that I know will work. So we've looked at a lot of things that have been based upon laser scanners, but this is not the only way to collect point cloud data. So we can use our aerial imagery, so a plane flies over with our camera capturing normal images, and we're able to process this to create point clouds using a thing called structure for motion, which is a way of finding same points in multiple images and working out their position. So you can create a 3D point cloud from that. Once again, I will attempt to show, I'll just give an overview from above. I won't zoom in to show too much detail, but you can see from here that this is an area of Southampton we've captured using the same approach as that I mentioned a moment ago. And this is billions of points here, and it can show clearly individual buildings and features covering large areas. So this could be really well used with a mobile mapping system that can only see along road corridors but can't see the tops of buildings. By combining these two data sets, you can get a much more improved amount of quality of data. We also can do the same approach using UAVs. So at Ordnance Survey we have two UAVs, or unmanned aerial vehicles, or often in the press referred to as drones. These are remote controlled vehicles, and we have a ABOT A6, which is a hexacopter, and a Germat G180, which is a fixed wing. And these could be in future really useful for our surveyors to go out into the field, to go to areas where, you know, it's not as easy to access. So we've got an image here of a sewage treatment works where it's not necessarily as easy to access, but by flying a UAV over, we can quickly capture data and then create point clouds from it in a fairly simple way. So this is created using Pix4D, which is quite commonly used in the UAV market, but there's also other software such as Agisoft PhotoScan that does similar things. So as you can see, I've shown you a good range of systems that you can capture things from, and they're a good way of displaying data in 3D. So this isn't 2.5D like a DSM or a DTM elevation model, but it's true 3D. These can also be used for further visualization, and really importantly, classifying this data can improve the number of things you can capture from point clouds. Classification isn't quite as mature as raster classification. There's a lot of programs out there that are currently working on this, but they're not, as raster classification has been around for a lot longer. It's a lot more mature, so it's still a lot of things going forward. There's some limitations with classifications. I'll show you in a moment just a couple of slides that show what a classification can look like, but it's definitely progressing. In the future, it'll be something that could be really useful. Meshes can be derived from point clouds, and these are a much lighter way of producing data, a lot more easy to visualize, and they can help with things such as line of sight modeling or signal propagation, which are things that we look at. As I mentioned, these can be used internally and externally, so you can combine multiple sources of data. And one of the interesting things that is coming forward is scan to BIM, so you creating building information models of as-built buildings. You can take one of these scanners around and find all the assets within the building without having to go through layers and layers of CAD drawings, or if they don't exist, then often you have to manually come around and capture everything by hand. So this would definitely aid building information modeling. Here is two examples of classification we've done. One, a aerial system on the left. As you can see, it's just done vegetation, buildings, roads. This is using a combination of vector data, but also some of the signal information. So the roads were captured using vector information, but the rest was classified from texture, color, and position. And on the right, we have an example of some of Trimble's mobile mapping that has been classified, so you can clearly identify lampposts, buildings, grounds, vegetation. So the options of taking this data and doing something automatically to improve efficiency and create products out is the future. It's got a lot of potential with this. I also mentioned meshes, and I'm going to attempt a demonstration now, and this is a mesh of Bournemouth created from an oblique camera, so like a ZAR CD30 oblique, an area of Bournemouth. And this is, you're able to scale up to huge areas and create really detailed maps. So this, as I mentioned, can be used for line of sight, it can be used for city planning, it can be used for signal propagation, it could be used for navigation, and it could just be generally used for visualization. There are a lot of challenges that relate to point clouds and things that meshes can address a lot of them, because, for example, point clouds can be, as mentioned earlier, can be billions of points, and as a result are very cumbersome, can be slow, so you need good computers to process them. By providing a mesh, you can reduce some of the quantity of data, which makes it a bit easier for machines that don't have the same processing capacity. And it can also enhance some of the scalability of the applications. So I've given you a brief overview of some of the things we're doing in business change and innovation, how to capture point clouds, and a few of the ways that we can extract data from. I'm going to have a look, see if anyone wants to ask any questions now. If you do that, if you can answer them now, and I'll do my best to answer them. So we've had a question which is, besides the obvious advantages of being able to view very high resolution data in the web, what are the analytical applications of point clouds? It's a very good question. I think I touched on it briefly, but to give a bit more of a detailed answer. So point clouds are a way of looking at true 3D space, both internally and externally. We can currently do what we consider to be 3D analysis of data, so looking at DSMs, but as these are only 2.5D, you can't see under trees, you can't see building overhangs, and you can't look inside buildings. So if we could find ways of classifying these data in the same way that we can currently classify 2.5D data, then we're adding a much greater dimension to the way we can capture data. We've also looked at driving meshes. We're working on a 5G project, so seeing how signal propagation can work within a city. So see how telephone signals travel around buildings that are closely spaced. So that could be used for the same application. We're also looking at using the mobile mapping systems to, as part of a CityVerve project, for example, in Manchester, we're looking at using this data to capture things from terrestrial data. So we're looking at features that are on the ground, such as lampposts, bins, information on parking spaces, a huge, vast detail of information that we couldn't send individual surveyors out because it would take too long to capture. Instead, we're able to have a mobile mapping system drive along and capture large amounts of data, which we can extract a lot automatically from, but then we can also have someone or multiple people in an office going through the same data and manually extracting features. So that's an idea of some of the projects we're working on that actually are currently utilizing them. But it is a very good point that when you see point clouds, a lot of them are just looking at visualization, because they are a fantastic way of bringing 3D to people who don't get to normally look in detail at geospatial data. That may be not considered to be an important thing, but if you looked at something such as city planning, you don't want people to have to look through long GIS documents and lots of pieces of paper to understand how an environment would look. If you can provide what the city would actually look like, or what a new building would look like, then this gives great enhanced ability to general members of the public. And that could also be used for things such as tourism, for people who want to see what an environment, do they want to visit it, get a real immersive feel of a place that has got 3D data of. I'll move on to the next question, asking about LiDAR and whether we have separate LiDAR to the Environment Agency. So at Ordnance Survey, we do not capture any LiDAR. So our two planes just have Ultracam XPs in, so just capturing imagery. We have been looked at some of the LiDAR data. So for anyone who's not from the UK, the Environment Agency manages a lot of the environmental aspects of Great Britain, and they recently had they created an open source data of their LiDAR, and this is a fantastic data set covering large areas of the country, and we've been looking at ways to see if we can work with the Environment Agency to enhance their offering, or if we could use some of theirs to enhance our offering. As I mentioned, we're not capturing LiDAR, but we're creating point clouds from things aside from LiDAR and using LiDAR where available. Hope that answered your question. Do you use any multiple return data of LiDAR which may add classification? So this going back to the LiDAR question, whenever we've got LiDAR, we'll always use the first last returns. So if for example, we want to create a DTM, a digital terrain model, looking at just the ground, so without buildings and vegetation, we'll obviously use the last return of that to create an elevation model. But this could also be used to find vegetation, to find things on the surface. It's really useful, and find out how dense information is. So we are looking at it, but it's not part of our current product creation strategy. But it's a amazing thing that contributes to the purpose of LiDAR. Just have a look, see what other questions are out there. I've got one coming back to, can you classify how can you perform classification and data extraction of street assets such as road markings, parking bays? Is this classed as a classification? Well, you can automatically classify some of the things. So, for example, I've looked at ways you can take out white lines. So using the color, or you could use intensity, along with such an elevation model, you can work out what points are on the ground and what are the right colors. So you can pull out white lines on the object on the ground. So in doing that, you can group the road markings to be a classification. A lot of the other street assets can be more complex. So, for example, if I take something like a lamppost, this can have many different shapes. It can be even have things such as CCTV on, and we cannot find poles and things like that from mobile mapping data, as I showed in one of the slides earlier. But it is much greater, more enhanced if we have some manual data capture on top. So if we use systems such as Orbit GT, it has the capability to do vector capture directly on the point cloud, as well as being able to utilize automatic classification from this. I think we've probably got time for maybe one more question. Is Ordnance Survey going to be offering this service as a data set? Well, it's a very interesting question. A lot of the work I'm doing at the moment that I've shown you is on research, but we're definitely working towards trying to, bring this to, if what we find to be extremely useful, we'll try and bring this as a product or service in the near future. At present, there aren't any, none of the point clouds are products. We're happy to show people them if they want to come have a look at them, or give an overview of what we've captured. But at the moment, we're looking at specifically things like scaling. So trying to take point clouds up to a national coverage can be quite challenging. And so before we offer a product or service, we want to make sure it can be scalable, managed correctly, and we're able to provide customers a really good service and value for money. Hope that covers your question. We've got maybe time for just one or two more. We've got a question of how long did the TIMS cart take to produce a data set in HQ? So that's the system from Trimble that is based on wheels and pushed around. We captured the ground floor, the majority of the ground floor, and the actual capture of data was as quick as you could walk, which is similar to the Pegasus backpack. So we walked around the ground floor in 5 to 10 minutes. However, with the TIMS cart, to bring this into our local coordinate system, we had to do an initialization phase where we left the TIMS cart stationary on a known GPS point to bring it into the correct coordinate system, and that took around 20 minutes of initialization. So to do the ground floor, all in all, it took less than an hour, but the data captures actually really quickly. So once you've started off, you could just keep walking at walking pace, and then you keep capturing. And as I said, that's similar to the Pegasus backpack, which you can walk at whatever speed you walk, it can keep up with your data. So it's providing you're not running along, it'll work. Also have a question of whether master map building heights is derived from LiDAR. No, it's not. It's not. As I mentioned, we don't have LiDAR of our own. So this is all based on photogrammetric principles, using deriving height from elevation models and combining it with our footprints. So hopefully that's run out of time now, but hopefully that will give you a good overview. And as I say, there are many more questions that pop in through, so we'll find a way of answering them all and sharing them with everyone so people can see some of them in the future. And my details are at the bottom if you ever want to get in touch future or get in touch with OS International or Ordnance Survey. We have a website with a lot of detail on that.